pezzo di metà che mi faccio proprio destination, proprio così alla buona. Metà.
Good. In 1 minute, is Alba aware that she's going to? Is she?
You're here, okay.
Yes, the first one is.
Ostia.
The first one last session. It's Alba.
A me che cazzo me ne frega?
That's fine.
Both
Yes. Bless you.
Fantastic.
Io già. Lei io già. Sai, non come si fa dire.
Okay, so we are waiting someone.
We're waiting for Luana.
Luana is not coming.
She's not coming? Okay, that's just the
So
four
we,
of us.
we have other people.
Okay, then we then.
Yeah.
Let's proceed.
Yeah.
Let's proceed.
Very good. Very good. Good morning, everyone. So we'll have a shortened session this morning because the first presentation has been moved to another session. So we have two presentations and then we will be on a coffee break before everyone. So we can eat and drink everything.
Marvelous.
Yeah.
Coffee.
So I will start by presenting the jury. So I'm Gauthier Charles from University of Brest in France. And today with us we have Camila Robetta from the University of Ancona, Martina Copari as well from the University of Ancona, and Tamer Abdelaziz from the local university of the Basque Country. So I think we can move with the first presentation, Alba. As you know, you have 15 minutes to present. When there are 2 minutes left, I will wave or make some strange faces to you so that you know that it's time to conclude.
So always stand here. Perfect. Don't go in front of it because I think people cannot see when we're on the street. And you have a microphone. So you just put your this. Also take this and move slides. Okay, good luck. Merci.
Okay, so good morning everyone. My name is Alba and I'm going to present you my master thesis about assessing detection ranges of static acoustic monitoring devices for harbor purposes using land-based theodolite observations. I conducted my master thesis in Atlantic Technological University, supervised by Joanna Bryan. I don't have them.
The point.
Yeah.
Sorry. I left it here.
Thank you. So, as you know, sound plays a fundamental role in underwater ecosystems, and many marine animals rely on it for their survival. Odontocetes are a group of cetaceans that can use echolocation. So this means that they can emit sounds like click, and they travel through the water. So when they hit some object, they waves back as an echo wave, and then they can listen these clicks and then analyze their environment acoustically. So generally, cetaceans are difficult to detect visually, especially harbor porpoises, which are small in size and exhibit cryptic behavior. However, they are very active and distinctive acoustically. So this means that they are known to echolocate almost continuously and to produce narrowband high-frequency sounds, which are usually clicks, ranging from 127 to 140 kilohertz. So these species are very suitable to monitor acoustically. And then static acoustic monitoring techniques, also known as SAM, are used to monitor them. They are very cost-effective and non-invasive approaches that can operate continuously, independent of weather conditions and also independent of daylight. There are two main SAM technologies, click detectors and full bandwidth recorders. So click detectors is, for example, CPOTS and its newest version, FPOTS, can use algorithms to detect and log information about clicks. And on the other hand, full bandwidth recorders can capture and store raw acoustic data, such as, for example, sound drops. Previous studies have deployed both acoustic devices types together, and then they have found differences in false positive rates, also sensitivities and detection ranges. So there are different methods to evaluate the detection ranges of these devices. For example, playback experiments that consist in playing hardware-purpose recordings along a transect at different known distances from the acoustic devices, or wild animal tracking using theodolite or drone observations. Although playback experiments are easier to perform, they are known to not account for variability in vocalization behavior. So, wild animal tracking methods may provide more realistic estimates of detection ranges. Because of this study aims to assess the detection ranges of 3 simultaneously deployed SAM devices, CPOTS, FPOTS, and sound traps using wild hardware purposes theodolite observations. So the study area was the Skerries and Causeway Special Area of Conservation that was designated in 2017. And then previous studies have modeled the occurrence of hardware purposes within the area, showing that they occur mostly in near-shore waters around headlands, and also peaking their occurrence in summer months. For this study, the data collected consisted in acoustic recordings at 2 different mooring locations and theodolite observations that were conducted from the 21st to the 28th of July 2021. From the 2 mooring locations, one was located closer to shore, around 600 meters, and the other one further away, almost 1,000 meters. And then in each of the mooring locations, the 3 static acoustic monitoring devices were co-deployed simultaneously. So, as you can see, CPOTS and FPOTS were co-deployed side by side, and sound drop just above on the same line. So, CPOTS and FPOTS were recording continuously, detecting clicks at a frequency range between 20 to 160 kHz. However, sound traps were recording on a duty cycle of 20 minutes on and 40 minutes off, at a sampling rate of 96 kHz and with an enabled high-frequency click detector at 576 kHz. For the theodolite tracking, these visual observations were conducted by 2 trained observers, and every time that a sighting happening, they were tracking each surfacing event with the theodolite, that is this instrument that you can see here. So every surfacing event tracked was called a fix. So for each fix, the time and the horizontal and vertical angle were obtained, as well as the number of individuals and behavior when possible. Furthermore, a quality score ranging from 1 to 4 was assigned to each fix to account for accuracy. So here, in the right side, you can see an example of a precise fix, or a grade 1, that was one fix that was recorded using the telescope of the theodolite, and then a normal fix, or grade 2, that was recorded using the external sight. And then, once we had the horizontal and vertical angles, we needed to convert this to coordinates of each animal. So, to do that, we used this formula to account for the total station altitude. So, of the theodolite station. So, we were taking into account the station altitude above the sea level, which was 14.73 meters, and to this, we added the theodolite height from the ground to the telescope of the theodolite. And then to all this, we were adding the sea level measurement closest in time in order to account for tidal action. Then, once we had this, we needed to calculate the distance from the theodolite station to each porpoise. So to do that, we use basic trigonometry, and then using the vertical angle obtained with the telescope, with the theodolite, and this total station altitude, we got these distances. And then, knowing the coordinates of the theodolite station, we were able to also obtain the latitude and longitude of each visual fix. And then, knowing also the coordinates of each mooring location, we were able to calculate the distance from each surfacing events to these acoustic moorings. Then, for the acoustic data extraction, for the C pods and the F pods, we use the softwares provided by the manufacturer, and these softwares contain a kernel classifier, which identifies click trains, which are sequences of a minimum of 5 clicks, and then it assigns to them different categories and different quality classes. So for this study, we only selected the narrow band high frequency categories and a high and moderate quality classes. And then for the sound drop, we use PalmGuard. This is a software that has an modular architecture. So this means that you can put the models that you want to do what you need. So in this case, to extract the clicks, we add the module soundtrack click detector, and then we also run a purpose basic click classifier, and then after that we obtain individual purpose clicks. So to make this output more comparable with the click trains, we only selected those clicks that were belonging to a sequence of a minimum of 5 clicks with an interclick interval of 250 milliseconds. And then after this, the acoustic detections recorded within 60 seconds of a visual fix were considered a match, and all these matches were visually verified. And then also binary code was assigned to each visual fix. So visual fixes that were acoustically recorded were ones, and visual fixes that were not acoustically recorded were zeros. And then based on distance sampling theory, we also modeled the detection probability as a function of the distance of the purpose to each acoustic device. To do so, we use generalized additive models, saying that the response variable was acoustic presence or absence, and the explanatory variables the distance to the animal to each acoustic device, and also the distance to the theodolite station as a mooring site. And then, once we fit the models, we obtain detection functions that were giving us the probability of detecting the purpose when it is at a specific distance from the acoustic device. And with these detection functions, we also obtain effective detection radius and effective detection areas for each acoustic device. So now, changing to the results. When we have a look at the theodolite tracking distances, we can see that the distances obtained from the theodolite to the purposes, most of the fixes were focused on the first 500 or 600 meters, so before the inner mooring, and few of them were recorded beyond the outer mooring. Then, now, having a look at the distances of the purpose to each acoustic mooring. When we have a look at the inner mooring, that is the orange one that you can see, we can see that most of the fixes were concentrated within the first 500 meters of the inner mooring, and then for the outer mooring, these distances were more widely distributed, and most of them were concentrated within the 500 and 1,000 meters away from the outer mooring. Then now, when we have a look at the acoustic detections, so here you can see the acoustic click detections that were plotted across the different 8 days of the study. So we can see that for most of the device types, these follow kind of the same pattern. However, if we pay attention to the ends that show us the total number of click detections per device, we can see that in the inner mooring, there were fewer detections than in the outer mooring. And also, if we compare the sound drop with the C pods and the F pods, we can see that sound drops recorded much higher number of detections than the pods. So this highlights the higher sensitivity of sound traps compared to pods, even more considering that sound traps were recording in a duty cycle and pods continuously. And now, having a look at the matching results, so the number of matches that visual fixes that were acoustically matched, we can see that for the outer mooring, they were higher than for the inner mooring, as well as the maximum detection distances, as well as the probability of detection. So this difference already indicates some kind of observer bias effect in the outer mooring. We need to remember that the outer mooring was at least 1,000 meters away from the theodolite station. So here you can see an example. This is the same click sequence here on the top of the FBOT software and here on the bottom for the PalmGuard software. So this acoustic detection was matched with a visual fix that was 613.4 meters away from the outer mooring. So given the clarity of this second click, most likely what happened was that there was another animal passing closer to the outer mooring that was not detected visually. Now, having a look at the generalized additive models, so we found significance for the variable distance to the acoustic mooring, so decreasing detection probability as distance to the acoustic mooring increase. And also we found the distance to the theodolite station to be significant as well, so decreasing in detection probability as distance to the theodolite station increased. And also we find a significant mooring effect, because also we found that detection probability in the outer mooring was higher than in the inner mooring. So now, we decided only to focus on the detection ranges that we obtained for the inner mooring because of the potential values of the ones for the outer mooring. So here you can see the effective detection radius and effective detection areas for the inner mooring. And we found that the radius was the one for the F-pods with 250 meters, then followed by the sub-drop with 208 meters, and then followed by the C-pod with 193 meters. These values for the C-pods and the F-pods are consistent with previous literature. However, for the sub-drop, in previous literature of TOT 2025, they found it to be the greatest. However, in our it was not the case, but we need to consider that in this study the sub-drop was recording continuously, and in our study it was recording on a duty cycle. So we might expect that if our sub-drop was recording in a duty cycle, was recording continuously and not on a duty cycle, we could have the greatest effective detection radius for the sub-drop. So therefore, this study highlights the higher sensitivity of sub-drops compared with pods. Also, the results suggest that detection ranges estimates may differ according to the sub-drop duty cycle configuration, and also that large distances between the theodolite station and the acoustic devices may overestimate detection ranges. So just to finalize, this study provides a baseline for designing effective acoustic monitoring strategies, taking into consideration device types, recording configuration, and deployment location. So here you have some references, and thank you very much, and I would like to acknowledge my supervisor, Dr. Joan O'Brien, and also Dr. Morgan Pumier for allowing me to work with this dataset and for all the support through the process.
Thank you very much, Alba. Who wants to start with the question, Joel?
Okay, I will just have one question.
Okay.
Hello, very nice presentation, thank you. I just have one question regarding like more of a curiosity, okay?
Yeah.
So from this acoustic data, okay, so what can you deduce from, like what results can you know about the animal just from the acoustic data? Because just like I like my knowledge is very little in acoustics, so I just very curious to know what can you get.
Mm-hmm. Yes, so the acoustic devices that we were using here, they were deployed for 3 months. However, we only considered the 8 days because it was the ones that were matched with the visual data from the theodolite observations. But for the 3 months that these devices were deployed, using this static acoustic monitoring, you can have a lot of information. So these are devices that are on the bottom, and then they can record continuously, independently of weather conditions, and also during at night time. So you can see the presence and absence of these animals according to different variables, as for example, tidal cycles, dial also cycles, so if it's morning, evening, day, night, or also different, for example, stations. Well, in this case, it was only 3 months, but yeah, you can also add some environmental variables or time variables in order to know, according to the acoustic presence or absence, if these animals are present or not here. And also, we were choosing this study area because this is a special area of conservation. So it's very important to have to know specifically what you have in this area, because these areas needs to be supported with a data that proves that these animals are there. So in this case, putting these acoustic devices could give you all this data that you need to know where the animals are, and what they do.
But can you know, like, for example, about the age of the animal, or just something very new? That's impossible.
No, age of the animal, no. So because in this case, it was so. In our study, we were only targeting hardware purposes because they are narrow and high frequencies. So they are very distinctive. So for example, for the C pods and the F pods, you can just like select that category, and we know that this species is the only one in the area producing this kind of sounds. But you have also some, for example, dolphins that they are broadband producers. So they can produce clicks ranging from few kilohertz to also quite high kilohertz, but the software already takes that into account. So we were putting like all the classifiers just to target these species. So in this case, you can only have data of presence or absence, but it's true that with the pod data, you can, and also with the sound trap, analyzing the inter-click intervals of each click, you can have some kind of know of the behavior that they are doing. Because these animals, when they are foraging and they are targeting one animal, they start to produce clicks more quick. And then these inter-click intervals reduce a lot. So this is called buzzes, and then you can see these patterns in the software. So you could also have information of the behavior.
Okay, thanks.
Congratulations for your presentation, Alba. Really clear. I just have two curiosity because I'm not an expert in this field. So actually, one of the questions you already answered, but I was wondering if you, with this method, you can discriminate the sounds among different individuals, or maybe among younger individuals and adults one.
So among different individuals, no, because they are all producing the same sound. So, but the thing is that, for example, in the approach that I was following here, so as we were matching the acoustic detections with the visual fixes, the data that we had from the theodolite, we were able to know the number of individuals. So these species, mostly they are found alone or with very reduced groups. So there was the number of individuals that I had for each sighting, mostly they were like 1 or 2 individuals, and 2 individuals were a mother and a calf, probably. So in this case, the need to identify like the clicks belonging to different individuals is maybe not very necessary. So, but yeah, you could not tell different individuals apart using this method because it is you have few individuals, but they are gonna go together, and then yeah, they are gonna collocate at the same time. So yeah.
Okay, thank you. And the other question is related with the deployment of the device.
Mhm.
I mean, the depth
Yeah.
was selected because of the presence of the mooring there, or there is a specific depth in which you have to position to allow for
No, so
detection.
in this case, I'm sorry, I moved, but I cannot. Yeah, so here the two different mooring locations, one was at 21.5 meters, and then the other one was at 25 meters. And we were not able to choose that because these acoustic deployments were part of other projects. So because of that, they were deployed like 3 months, and then we only take advantage of this data using the 8 days that we were conducting. Well, I was not collecting the data, but the girl that was collecting the data only collected the data within these 8 months. So yeah, in this case, the depth it was not taken into account, but it's something that you can take into account because there are some studies that show that the acoustic detections can change in depth, and also, well, it depends on the topography of your study area. But as I was discussing here, more depth probably you have like the mooring location farther from shore. And then farther from shore will mean that you will have less accuracy in the distances that you are calculating, and probably that your detection ranges estimates will maybe be not so accurate. So yeah, it's an important factor to take into account, but yeah, we were here working with what.
Thank you.
Congratulations, first of all. Very, very nice presentation, the visualization as well. So these differences that you observed also in the radius that they can collect, how can you explain this since they are the same devices positioned in the two moorings?
Yes, so C pods and F pods are built by the same manufacturer.
Okay.
And then we know that CPOT is the older version of the FPOTs. So FPOTs already were able to increase the sensitivity of the devices and also the detection ranges. So we were expecting FPOTs to have better sensitivities and better detection ranges. And also soundtracks, we know that they are also more sensitive.
Yeah, but between the two moorings, you say that in
Ah,
the one
between-
you have
Okay.
500 radius, and the other
Yeah.
one 1 kilometer more or less.
Yes, okay, yeah.
Since they are the same devices positioned in
Yeah.
the two moorings.
So,
Yeah, that one.
so here, the thing is that we have, oh my God, I'm just,
You can also close it.
yeah, okay. So here the thing is that first we need to have a look at the visual fixes overall distribution.
The visual is the one of the observer.
Yes,
Okay.
so here we can see that most of the fixes were located near shore. So then, if we consider that the inner mooring was also located near shore, it will be, so the matching of these acoustic detections with all these visual fixes will also be located within the 500 meters, because most of the visual fixes are near shore and the inner mooring is also near shore. However, if we consider this outer mooring, this outer mooring will have these visual fixes located farther away. So because of that, most of the fixes detections were located far between the
So
500
it's
to 1,000
not that
meters.
the two had a different radius, it's just because of the position. So if the other one was positioned farther, okay, so
Yeah.
I didn't get
Yeah.
it, okay.
Yeah, and it's the observer bias that I was talking about, because also so the effort was not the same. So here you were expecting to have maybe visual fixes all over the place or uniform to have a better effort, but in this case they are focused near shore, so because of that, yeah, we have this observer bias effect here.
And these were also registering the noises of boats and stuff.
Yeah.
How did you clean? And were you able to discriminate because of the length or the length of the waves, or?
Yeah, so for example, for the F-pods and the C-pods, this software, using the kernel classifier, that identifies the click trains, it assigns different categories. So according to the origin of the sound and the quality of the sound. According to the origin of the sound, you can discriminate between narrow band high frequencies, sounds, also broadband sounds, for example, some dolphins, and also sonar or anthropogenic sources.
Okay.
So just selecting the narrow band high frequencies, we were already sure that we were not accounting for sonar or anthropogenic sources. And then for the soundtrack, we were first running the click detector, so we were just selecting the clicks. But then we know that from some sonars you can also get some clicks. And then to ensure that those clicks were from porpoise, we were running the basic click classifier with the default settings of porpoise. So the software has already some default settings for porpoises that you can put. Of course, these techniques, one of the limitations is that they can have some false positives.
Yeah.
But in our case, as we were matching this with the theodolite observations, we had few matches, and then I manually verified all these matches.
So you had to listen to the.
Not to listen, because these softwares, the CPOT and FPOTs, it's only visually.
Okay. No, that's fine.
Yes, so the manufacturer provides some protocols that you can identify the pattern of the clicks and also the interclick intervals and also the amplitude. You can see different parameters, and then you can kind of identify if that detection is from the source that you are targeting, so for harbor purposes source or other source that can be false positive. Yeah.
Thank you.
Thank you very much. I have 2 minutes to ask a question myself. So, I was wondering about the effect of weather and sea conditions. Did it have an effect?
Yes, so I did not mention that, but when they were conducting the theodolite observation sessions, they were also recording environmental conditions every 15 minutes. So they were recording visibility conditions, sea state conditions, wind direction, wind force, and also swell height. So we in this study we only selected the sea conditions that were below 3 in the Belfort scale. Why? Because these harbor porpoises animals, as I told you, they have like a very cryptic behavior, so it's very difficult to detect them visually, and even more if you have high swell height or a lot of or in the Belfort scale, it's like more than 3 that you already have like white caps, and it's more difficult to detect them. So we were taking into account the weather condition with this during the visual sightings. And then for the acoustic detections, yeah, maybe if you have more wind or more swell height, maybe you have like more sound in the surface that can also affect the detections. But in this case, there was like not need to account for that because, yeah, we were just like extracting the data.
Okay, thank you very much, Elda.
You're
Congratulations. And we can move on with our next presenter,
Was it stuck in your hair?
Lorena.
Take your time.
Such a good job. Thank you for explaining some things. That will have to be-
You had a PowerPoint and a PDF. You
Yes.
prefer the PowerPoint?
If the PowerPoint is working fine, yes, because I have some like little videos in here.
The PowerPoint will work fine, I think.
Are you sure?
We will see. Normally, I already checked, but I didn't see it.
Yes. Right. Okay.
We cannot test it. See if it doesn't work.
If it doesn't work, I'll switch to the PDF. Is that possible?
See. It will work. So this is the pointer.
Mm-hmm.
You put like this. Yeah.
So, Alba, you have the congratulations of Morgan. Salut, Morgan.
I'm struggling to figure out how to
Well,
do this.
It's just you put it on your ears.
Yes, but it's stuck in my. We will start eventually.
Very difficult.
So,
Okay.
so Lorena, you have
We have
15
time.
minutes, and I will wave at you
Okay.
when there's 2 minutes left.
Okay. Lovely.
Whenever you're ready, the floor is yours.
Okay. Good morning, everyone. My name is Lorena, and I'm going to present to you my master's thesis, which is From Presence to Behavior, Dolphin Acoustic Responses to Noise and Environment in the North Channel. So the ocean is far from being a silent place, from offshore installations that are not showing up on my slides, shipping activities, military sonars, wind farms, and occasional yellow submarine, as well as marine mammals and marine life, from like crustaceans to fish and meteorological events. We get actually quite a loud ocean environment. Sound is incredibly important for stations. They produce, as Alba mentioned, click, whistles, and pulses, and the ocean is getting louder, with, for example, shipping having more than doubled since 1965. And these have a lot of potential impacts on cetaceans, from the masking of their interspecies communications to behavioral shifts, for instance. And so passive acoustic monitoring has been increasingly used in acoustic studies for stations, which basically consists of placing a stationary hydrophone deployed underwater, which records continuously over a month. It's non-invasive, cost-effective, and for the long term allows us to both capture ocean soundscape and ocean noise, as well as cetacean acoustic activity. So this is an example of a spectrogram that you would get from passive acoustic monitoring with like a dolphin whistle in there. And so passive acoustic monitoring has mostly been used to measure presence. However, it would be interesting to kind of take the full potential, because there's so much information that we get from raw acoustic audio, and kind of take a more behavioral approach and to look more maybe qualitatively and more with maybe more further ecological insights. But a lot of behavioral studies in this area have used different methods, more experimental, more short-term, or not necessarily using PAM. So there hasn't been a lot of long stationary PAMs that compare acoustically derived metrics with a behavioral perspective and models it against chronic ocean noise. And there's a call in the literature to really push passive acoustic monitoring to its full potential. And so the research project used sound pressure level with passive acoustic monitoring. And with passive acoustic monitoring, we also measure acoustic metrics. And so the idea is to kind of compare how different metrics that we get from this data. So presence, and then with a metric based on whistle rates, so based on like the number of whistles and like level of activity, as well as the presence of buzzes and pulses, which are indicators of foraging behavior. So I have quite a lot of objectives with this. I wanted first to assess the relative influence of environmental conditions versus sound pressure level, so noise. I also wanted to characterize the nature and direction of dolphin acoustic responses. It was also interesting to identify which sound pressure level frequency bands were more strongly associated with responses. And all of that allows us to evaluate how ecological interpretation can vary based on the metric that was investigated. And I also wanted to develop a confidence-based validation framework for automated passive acoustic workflows. So the study area is part of a project funded by the European Union. It's called the Straits Project, which monitors marine life in 4 different straits in Europe. And it's located right there between Great Britain, Northern Ireland and Ireland. And this is an area under a lot of anthropogenic pressure with wind farms, offshore installations, dredging, and quite intense shipping around. So we deployed a hydrophone underwater. It was deployed from May to October 2024, and it's operated for the first 15 minutes of every hour because it takes raw audio data, so it cannot have a continuous recording cycle. And so that was a total of 1,086 hours of raw acoustic data. For acoustic analysis, I used PalmGuard, and that transformed raw audio into spectrograms, and then it detects whistle contours and turns it into a data set that can be then further validated. And so that's an example of a spectrogram of whistles again, but this one I'll show you the highlighted whistle contours that the software detected. I also did some validation work because as great as PalmGuard is, it makes some mistakes, and there were a lot of false positives. So using things such as frequency range, the duration of the detections, or the event effects, I was able to assign confidence level scores. Also buzzes were detected kind of using temporal overlap, a similarity in duration and center frequencies, since there are this very tight stack of short sounds that are all happening kind of like on top of each other. And see, these are basically very fast click trains. Oops, I went backwards. Also for sound pressure levels, so ocean noise, I divided it into frequency bands. The most interesting one for us are the 3 on the left, and that's where I did my primary analysis. The very low frequency one is where a lot of shipping noise occurs, and it also mostly falls outside of dolphin hearing range. So it's interesting to see how that could definitely impact dolphin acoustic activity. And then we also have low frequency and mid frequency bands, which would contain a different array of anthropogenic sound sources. So I have 3 response variables. I have presence, I have whistle rates, which is based on counts, and I have the presence of buzzes, which indicate foraging. I have sound pressure level variables through different bands. I have environmental variables as well. And I use generalized additive models that were selected with AIC's model selection. And that was a total of 50 generalized additive models that were used in the primary analysis. So, for the results, first I wanted to look at what does the soundscape look like. And what we see here is that the very low frequency actually dominates the soundscape by about 10 decibels compared to other bands. In some days, it also reached over 110 decibels, which actually is quite loud. It's hard to really understand what it feels like underwater. I also quickly investigated kind of the temporal train of sound levels during the deployment period, and I saw no obvious temporal pattern. So the key message here is that low frequency kind of tend to dominate the soundscape here kind of throughout the deployment periods. I quickly also looked at an exploratory way, looked at different acoustic metrics through time. And I won't go through all of that, but for example, I just wanted to highlight that on the bottom left, if you look at high quality whistles per 15 minutes, so that's whistle rates, it peaks in June. But if you look more at the density of whistling events, it peaks in August and is almost the lowest in June. So already there's a hint that the metrics can tell different stories and can yield different results. For here, I just wanted to highlight that basically the most recurrent significant predictors were dial phase, so morning, evening, night, NPPV, which was net primary productivity, sea surface temperature. So these were kind of like some of the key environmental predictors in our models. Now, so remember how I told you I did 15 models? So let's focus here on the big picture, because there's going to be a lot of gaps explained, but essentially I just want to look at overall trends for now and how that compares to our metrics. So for presence, we see that we have relatively weak effects from the sound pressure level, and that these are overall linear and negative. We also see, now that if we look at environmental variables, we have stronger statistical support and what seems to be stronger effects, and we have more complex effects as well. Now, when we looked at rate instead of simply presence, we kind of see a similar pattern here with linear and negative relationships from sound pressure level, but for the very low frequencies, those were even weaker, where delta AIC was negative, which means that the models perform worse when we included this variable. So the effects of SPL is relatively weak. And once again, if we look at environmental variables on the side, we see that those had stronger statistical support and also showed more complex responses. And last but not least, now looking at buzzes, similar kind of patterns with sound pressure level, negative linear but relatively weak, and more complex responses and strong from environmental variables, and these are which were more statistically supported. So to summarize all of this, because this was overwhelming, we have very low frequency bands that was only significant for just simple presence, whereas the low frequency and mid frequency band had significant impacts on all of the metrics. Those impacts were relatively weak if we compare to environmental drivers, because environmental drivers drove like 5 to 20 more, explained 5 to 20 more times more deviance in the observed responses. So the sound pressure level bands overall have a negative impact, but it remains relatively weak and acts more like on top of environmental patterns. And the key message here is also that different responses showed different level of first like statistical support, but they mostly also showed different responses to environmental variable. Oh, I went backwards again. So here, that's why I went to the PowerPoint, because I was hoping to make you listen to a little bit of like what that actually sounds like, and I'm not sure if that's gonna work. So here's first of all like what would be like a very high intensity like whistling event, and I'm just hoping that there is sound. Maybe not. Yes.
There is sound.
So that's like high intensity, but like as you can see on the bottom left, they also exist in isolation. And I also also wanted to make you listen to is like what a buzz sounds like. So it's a bit subtle, but they're quite strange. Yeah, it's very subtle, yeah, but it's like this sound. And so that's what I listened to for 3 months. So continuing this, let's discuss a little bit our results. First, basically the overall message here is that environmental drivers are the main predictors for the patterns that we see. Noise still has impact, but the chronicle elevation for decades may show that this impact is not reflected in our dataset, and also like loud impulsive noise are not necessarily reflected. So this is consistent with the literature and generally with also the idea that environmental conditions shape ecological processes in different life cycles, from like foraging opportunities, seasonal movements, or like reproductive behaviors. Now, the shapes of those responses varied a lot. This is a quick summary of all that we found from the results. But for example, if we take for net primary productivity, we had a U shape for whistle rates, and that indicates that high productivity may have shifted often towards foraging, so maybe moving away from social activity, whistling less overall, but so concentrating maybe more on clicks and responses. We also saw negative impacts from sound pressure level, and this does this makes sense because there's so the process of acoustic masking, so whereby whistles will have to become louder and longer, so they're like more costly to produce, so that might result in an overall decrease in whistling rate. There's disruption of social activities, and these have a bunch of ecological consequences, from weakened social cohesion, energetic deficits if foraging is disrupted, as well as displacement to suboptimal areas, for example. And all of that can have population level effects. So also we saw that the very low frequency band had generally a lower impact than the other ones, and the very low frequency band is the one that is outside of dolphin hearing range. So hearing overlap matters more than the overall sound energy that is produced. So that must be taken into consideration in management, like that overlap with the hearing range and hearing sensitivity is very important. Our fourth objective was to evaluate how ecological interpretation changes, and for example, when we looked at rate instead of presence, we saw that the explanatory power changed. So we see that, for example, maybe in some studies, like we can maybe underestimate the impact of for example, like noise on dolphins, because I think with whistle rate we get like more like quantitative. Quantitative, but like continuous information instead of like binary information. We also have different environmental patterns that we're seeing, where, for example, like we had a whistle rate peaking in June, but buzzes peaked in August. So that shows that different metrics can tell us potentially different ecological and behavioral stories. And that matters because behavior might be impacted before presence. And so we need to take that into account as well and look at those impacts as well. And one metric is not enough, and we need to push back towards its full potential of looking further than presence. For my fifth objective, I did the validation framework. I haven't gone through that much, but overall it reduced my false positive rates, and it showed relatively low sensitivity to thresholds, meaning that ecological conclusions did not change much based on the confidence level chosen. So overall, it was a 6-month single station study. I haven't looked at the winter yet. I only used one device. I have not looked at very finer resolution at the data as well. So that's one limitation that would also be interesting to take into account and do further work. Also, I haven't been able to distinguish species. So using species-specific classifiers in future work would be really interesting, though they are very challenging to apply. And testing interactions between different variables as well, and combining the data, for example, with visual observations from behavioral observations with what the acoustic reality is would be really interesting to really make even stronger behavioral inferences from this type of data. And so the management should then prioritize frequency ranges like anthropogenic noise and mitigate it in the frequency range that overlap with dolphin sensitivity, and regulate impulsive sounds in moments, for example, that matter more for dolphin acoustic activity, like, for example, with the peaks in the summer. So yeah, thank you very much. I hope that was not too overwhelming, but I'm sure you have questions, so I would be happy to take them.
Thank you very much, Lorena. 15 minutes, exactly. Who wants to start in the journey? Okay.
Yeah. Thank you. The presentation was really, really nice. I'm not an expert on this, so I'm sorry if I ask a question that maybe you already said, but I mean, differently, you weren't able to discriminate between species. So
Yes.
you would consider dolphins in general.
Yes.
Okay.
So though in the area, common dolphins, Shortby common dolphins are the most common. So these are the species that we would expect to find, but it's totally possible that in some of the recordings there's bottlenose dolphins as well. They are more rare in the area. But yeah, of course, like there's like species variation that can influence the results as well. There's also like migration. So some species, for example, would potentially, and that's not necessarily so strongly the case for this area, but in further PAM studies that would apply similar methods, some species would move towards the continental shelf, for example, maybe in the summer, while others would come because their prey would be here at that time. So you would have a shift in species composition potentially. So that's important to take into account. But yes, at this point, there are species classifiers that exist. I have applied one. It's yielded really strange results of species that are nowhere near this area. And so it would be interesting, but usually you would need to train those classifiers on your data and combine it with visual observations, and that's extremely time consuming.
And differently from the devices that Alba used, you were able to discriminate between individuals or not? Is the same?
No, it's not possible. Yeah, because the only thing I have is sound, and obviously there's potentially some inference to be made, and that's where I think we should push Pam to try and use metrics such as rate and not just yes there were whistles, but there's obviously a lot of limitation because if I hear 500 human talk at the same time, there's no possible for me to tell if it's 100 or 200 or 300. It's really hard to tell, but I have an idea of I know it's not one, so that's already yes, yeah. But it's very limited and very subjective to interpretation.
And maybe I lost it, but at what depth did you put the device?
Oh yeah, I was at 70 meters.
70 meters.
Yeah.
It was based on literature or just.
So I did not do that myself, but basically it's just because so on the contrary to Alba, which your station was like really close to shore, mine was like I think I have a lot of slides, so this takes a lot of time. Yes, right here. So like compared to Alba, like it's still relatively close to shore, but I'm way more offshore. So of course the depth is going to be deeper. But at 70 meters, that's definitely like a depth with which dolphins would operate. So.
And it's a mooring station as well, or they just.
Yeah, it's a mooring station as well. Yes.
Okay, it's a mooring station as well. Okay, thank you.
Okay, I have one question on the methods, and that is just written here. The 15 minutes selected, it's based on literature, or you choose these 15 minutes to analyze because otherwise it will be really too much to analyze all the data.
So the 15 minutes is a property of the device. So because this device like has raw audio data and it also has a limited battery life, if we were recording, if it was recording for the whole hour, it wouldn't be able to last 3 months. So it's a property of usually like I have the RTCs, but the sound traps that Alba uses as well have the same system where they will record from 2 p.m. to 2:15 p.m. and then from 3 p.m. to 3:15 p.m. And that's just the way the devices function. Otherwise, the battery life would run out and the SD cards would run out super quickly.
And I would like to go a little bit deeper on the interpretation of the discrepancy between the buzz, I hope I pronounce it right, that are concentrated in August and the other result that was concentrated in June.
Yes.
Could you go a little bit? Could you explain a little bit more deeper this discrepancy in the results?
Yes.
I mean, how could you interpret this discrepancy?
Yes, I think just to have like a visual support. I think this one could work. Yes. So for instance here, so we have so the whistle rate metric that I used. I actually had a lot more metrics that I calculated. So I calculated maximum event density, and I think that's an important one actually. So that basically whistles would be accounted to be within the same event if they are within 30 seconds of each other. So that creates a whistling event. And so the total density of whistles within that time is like the density. And then for high quality whistles, that's just the number of whistles per my 15 minutes of the recording. And then there's the presence of buzz. So these are some of the metrics I calculated. So the high quality whistle rate I use for the main analysis because it's also like the simple one for I think for steps. It peaked in June. And buzzes actually had the presence of buzz was actually lower in June and higher in July, August. And so that actually coincides for moments where the sea warms and where there's increased in primary productivity. There's also literature that suggests that in this area there's migration of some preys to this area, like mackerels, for example. So that foraging would increase at that time. So we would think that, I think quite naturally, like if they are foraging, they need to cooperate, they need to talk to each other, communicate, and maybe not talk. So we would think that, but actually this result suggests that overall there is less vocalization, and that maybe we see that there's also like a peak in August with the density of whistles, and maybe they communicate overall less and spend less time socializing. And when there are more praise available, they spend more time focusing on the clicks and the buzzes rather than having long extended periods of social activity. There's also, for example, potential like peaks for certain populations where mating could occur earlier in the summer. Obviously, like all these interpretations are like purely speculative at this point, and that's why some more visual data would be really helpful in understanding, for example, when foraging, do they whistle more overall than when they are social? So yes, so it's kind of a priority between foraging versus other. One interpretation is that in June they're socializing more, and because they spend less time foraging. But obviously, like that could be mating behaviors. That could be group size that simply was higher in June, and some groups left. At the end of the day, it's pure speculation because there's no additional data to really compare. But it's a first idea that yes, indeed, different metrics, and if we looked at density or like just the number of whistles, and we get different results. So yes, I don't know if that answered your question. Yes.
Perfectly, thank you.
Okay. I have a question regarding. So you said that like you cannot distinguish between the species of dolphins, right?
Yes.
But is it like is it because of the limitation of the device itself, or because that was like out of the scope of the study?
It's a limitation, not necessarily of the device, but just of the methodology of acoustic studies. There are species-specific classifiers that can be used, and those are kind of work with sort of like artificial intelligence, like algorithms that were developed to classify based on the shape of the whistles, for instance. And so yes, it's because it's a limitation of the device, and assigning species is something that people are trying to do. It's very complicated, and so I tried. But it would, at this point it fell outside of the scope, and it would be nice, I think, additional work that I would like to do. But yeah, at this point it's something that would need to be taken into account as well, especially if you want to look at behavior and take the full advantage of PAM, which is kind of the point I'm trying to make. But at this point it fell outside of the scope of the primary objective. But it is a limitation. Like if I did it, it would remain exploratory, and it would remain like sort of like methodological trial and error, rather than applying a method that is confirmed and relatively easy to apply.
Okay. I have also another question regarding the results between like when you try to use the model in order to correlate between like the environmental variables and the clicks or the results that you are having. So did you see, like, correct me if I'm wrong, like did you see any correlation between like the sea surface temperature and clicks?
Yes. So I haven't gone too much into details about it because I ended up running a lot of models. And in the end, I mean, that's the things I was to compare how different eclipse response give us different information. So I didn't dive too much into it. But yes, for example, if you look at presence, you see there's like a positive, like complex, not fully monotonic relationship with sea surface temperature. And so that kind of works with like when we saw peaks in July and August, which is when temperature peaks in the area. For example, with whistle weights that peaked in June, then we have a preference for the intermediate temperature here. So there's this kind of like dome shape. So peak in June is hot, but it's not that hot. And for buzzes, it was actually a positive linear relationship. So yes, there's definitely like quite strongly actually supported correlation with sea surface temperature, but also productivity with my metrics.
So do you think this is mostly because like maybe during summer they are more active, or why do you think really that temperature can affect like that? Does it like regarding activities or what?
Yes, usually in the literature it's attributed to prey availability and increased productivity in the summer with increased sunlight and warm temperatures. But also there's also other phenomena like prey migrations, prey that move to the area, for instance. So yeah.
Thank you.
No problem.
I have 2 minutes again. No, I can.
Sorry.
It's not about anything. Okay. So you're showing us some figures here that raise some concern. How can you explain the influence of the tide range on the buzz presence?
Yes, so the tide range is it's been like tidal conditions are relatively easy to obtain, so it's actually been quite studied in the literature. And so for intermediate tide range, so there's kind of again, you know, like interpretations of why this could be, especially like with having this sort of like intermediate preference. I'm going to talk about fast, for instance. And so intermediate tide range, so the tide strength would be intermediate as well. And so that means that you would have enough current to aggregate prey in specific areas that are predictable for dolphins. So the influence on tide on prey aggregation is kind of definitely something at play here. But then like the energetics of swimming costs as higher tides might also mean that it's very strong, that during very strong tide events it doesn't become very energetically inefficient to forage. So yeah, it's kind of like this balancing of different phenomena that has been attributed generally.
Okay, don't you think it could be some artifacts due to the structure of your dataset? Because you're running a lot and a lot of GAMs,
Yes.
which increases the risk to get some false positive effects.
Yes.
And I mean, I'm not very I'm not a specialist of, that kind of topics, but I'm not very convinced by the ecological basis of this relationship. So yeah, I can understand the relationship with surface temperature. I can understand the relationship with primary production, but the one with tide range, knowing that we have marine mammals that feed on fish that are slightly affected by tide currents, I'm a bit skeptical.
Yes.
That's well.
Yeah, I mean that's true.
I'm not saying you're wrong. I'm just saying I'm not convinced.
Yeah. I mean that's also like one of the things of like those GAMs. I mean those GAMs are also run on data that's I haven't gone much through it, but like that has a lot of limitation. Like my detection of buzz is not perfect as well, but also like if you see the performance of the GAMs, it's not performing extraordinarily well. Like the combined partial deviance of all the environmental variables combined together for buzz presence is 5.2 to 6.7. Which is not incredibly high. So yeah, those GAMs are heavily limited, and yeah, it's kind of like at this exploratory stage right now, more like not diving into the GAMs too much, but saying okay, if we use different metrics, we do see different things though. But yes, of course, there's a lot of GAMs where we run, and buzz presence is also like very zero inflated data. So that definitely also means that those like statistical interpretations are definitely limited at this point.
Okay, thank you very much, Lorena, and congratulations.
Thank you.
So we are already on a break, coffee break. Just please keep in mind that your colleagues are still defending, so please avoid going on a terrace and starting talking loudly. Just respect the weather.
Check this in.
Reading session 5. Well, I wouldn't want to do it. Session from this year.
So we will start our last section of today. The one that is so here. Then we have presentation from I will introduce the network that we like first to discuss the results. So this one what are we using the presentation? Are we going to do this presentation for 2 minutes? Okay. Good morning, everyone. Thank you for being here today. My name is Sol, and today I'm going to be presenting my master thesis entitled Greenhouse Strategies in Commercial Diversity. This strategy can simulate feed rate in the recommendation. This study was done at the NEA in Vietnam under the supervision of the First, I'm going to start with some introduction of the study. Vegetative coastal ecosystem, including mangroves, submerged syrup meadows, are commonly known by blue carbon ecosystems. They have a really important role in the global carbon cycle, and together they sequester more than 55% of marine organic carbon. Syrup meadows are especially remarkable by covering less than 0.2% of the ocean surface. They account for 10 to 18% of carbon. These made them a target habitats for nature-based flood mitigation solutions. However, their main climate benefits are not straightforward. Serious ecosystem, including their microbial associations, that sometimes can even kill them, such as carbon dioxide, methane, and oxygen. Methane is particularly concerning because the global warming potential that it has is 28 to 80 times greater than the one of carbon dioxide. So this leads us to the question. Is there carbon sink can be offset by the source of emission? To answer this, we need to accurately account for the greenhouse gas, which is exactly what this study is. Frambosa is our study species. It's a fast-growing species which inhabits shallow Mediterranean connections. It has a wide thermal tolerance, and it has been reported to be vulnerable to mining pollution. Some studies report effects in the action of the cigarette, as well as in the recovery effect after returning to vegetable temperature. Mining heat waves not only occur in summer, as they can also occur in winter or in early spring. This can be a real threat to these species because in winter they are below their thermal optimum and also they are in a colonization state. So here we find another gap of knowledge, which is what is the maintaining response of carbon dioxide emissions until these threats. So the objective of this study was to evaluate the effect of assimilating winter heat waves and carbon dioxide on liquid fluxes in single ways. We propose three hypotheses. First, the vegetation. That the vegetation will influence the greenhouse gas emissions in comparison with person. Second, the warming effect. That the warming will increase the greenhouse gas emissions. And third, the recovery effect. That after returning to baseline temperatures, the levels of emissions will return to baseline. For answering this hypothesis, these are the materials and methods that we followed. The sampling site was a semi-closed inlet next to the irrigator switch in Mallorca. It has a thing of a needle, and the water depth was really shallow. So this characteristic of the place made it really vulnerable to rapid water change. Here we performed the core extraction, where we took 6 vegetative cores and 6 unvegetative from the long of pressure. We also extracted sediment cores for another course for analyzing the sediment in the habitat for temperature. Once in the lab, cores were placed in 2 tanks. Tank 1 was the treatment, which was being experienced at 15 degrees, and tank 2 was the warming treatment. To control temperature, we used a water bath that was surrounding the cores, and temperature was controlled on the core with different heats at the start. We also had two other tanks, one with water reservoirs that were placed at the sample, which was at the controlled temperature, and the other one with water reservoirs that we put at the same temperature as the warming treatment to ensure that when we perform the water changes between incubations, they were at the same. In the warming treatment, this was the thermal reading that we followed. First, there was an acclimatization period at 2 degrees, which was when it changed to control, and then we performed a stepwise warming where we increased 2 degrees every 2 days, peaking at the 25 degrees. Then we turned back to the baseline levels, 2 degrees, and we started the recovery. In every step, we performed gas lattice integration. For these gas lattice integrations, we use a liquid result analyzer and electron field system, where we could measure carbon dioxide and concentrations. We also perform a metabolism equation where we measure the changes in dissolved oxygen during a period of 24 hours, and with these values we can calculate these carbon metabolic rates, the atomic interaction, the nuclear respiration, and gross partner interaction. In the field, we also perform some pre-replicated equations with the same system, a closed loop with the liquid breakdown. We also characterize the environment both in the field and in the lab. These were the parameters that we studied. We also measured the biomass of each core to be able to normalize the gas fluxes and the segment characterization to better understand the complex effects. Now moving to the results and the discussion of them. First, to validate our experimental setup, we compare the incubations performed in the field with the first incubation performed in the lab. In this way, we didn't find significant differences in them, and we can conclude that the core extraction did not have an expressive effect, and that our laboratory setup at 15 degrees at the baseline served as an accurate proxy of the natural environment. In this way, we can validate. We also validated the control treatment. For doing this, we checked that there was no temporal effect
and we could ensure that our control was actually quite control of the situation. And we didn't find differences between the temporal effect. So we could conclude that all the changes found in the warming treatment are due to the increase of temperature. Now, moving to the core of the results, I'm going to start with carbon dioxide. In this graphic, we can see the carbon dioxide plots and the increase of temperature. In yellow, we have the sediment and the thesis, and in green, the vegetation. For their sediment, we didn't find a response to the increase of temperature. While in the vegetation, we went from positive values during the emissions to increasing values in the absorption. So the function of the vegetation switched from source to a sink. These results were not what we had hypothesized at the beginning, because the warming, instead of increasing the emissions, enhanced the carbon free function. For explaining these results, what we hypothesized is that actually the increase of temperature we perform in the heat was taking it next to its thermal optimum, because the baseline was in the lower thermal range that they are in. So instead of providing this effect of emissions, it stimulated productivity. Moving now to different practice, we have the same graphic of different practice in this case, in yellow the first segment and in second. And we can see that the main effect in methane was the presence of the vegetation. There was a switch in the dynamic of the sediment when it's undetected, it was all the time negative values, meaning that there was more emission and negative absorption, as in function. And in the vegetation, it was all the time emitting methane, and actually it was increasing the temperature of temperature. So this has been reported in other serious species, but they always attributed this difference due to the higher organic matter in the sediment of the vegetation plants. However, we studied the organic matter in the sediment, and we found that it was really low due to the characteristic of the sediment in this kind of rich in the minor temperature. And also, we found that the difference in the organic matter between vegetation and vegetated didn't follow a pattern and was not significant. Here we have the organic matter content in yellow, the sediment and in the vegetated, and we didn't see a difference either in the depth distribution of the. So how do we explain that in vegetation the emissions of methane were higher? Well, we hypothesized that it could be due to the expression of ladder sugars, such as sucrose, into the right. It has been reported for other species, such as Popular Mechanica, which reported 8 times higher concentrations of these ladder sugars in their sediment compared to their sediment. These kind of sugars cannot be captured by the organic matter test that is performed, that was loss of emission, and they are a substrate for microbial metabolism that they produce methane, such as the methyl bacteria that use this methylated compound from cigarette. Another important result that we found was an interaction between temperature and biomass for liquid plastics. In this graphic, we have the plastics, the total biomass of each port, and we read of the warming treatment and in blue the control treatment. For the warming treatment, we found that the higher was the biomass of the vegetation, the higher were the emissions. This is in accordance with previous literature that reported a positive trend between biomass and emissions. However, the control reported the opposite. The higher was the biomass, the lower were the emissions. So we hypothesized that this could be happening due to a process called the radial optimum loss. At 15 degrees, the volcanosa is producing more oxygen than it's consuming, and this oxygen surplus might be going to the rhizomes and from there to the sediment through radial oxygen loss. When the biomass is higher, there is a stronger oxygen pump, which can create an aerobic environment that stimulates methanogen bacteria that can circulate, explaining the decrease in the concentrations. We can find evidence of this proposed mechanism that explains the result when we look at our metabolic operations. Here we have the net vegetation effect on the net production. So in this graphic, we have the three points where we measure the metabolism in root control and in red warming. And we can see at T5 that the control was producing more oxygen due to the positive value than it was consumed. So this could be in accordance with the hypothesis that this oxygen surplus is the one favoring the metabolism. Now, moving to the recovery effect, we found that there was full recovery in all the variables that we measured. They all returned to baseline levels when we returned to the degrees of the baseline. Here we have the carbon dioxide, but we can see the subtract, and on the metabolic rates, we can find differences between the first and the last. It's also important to know that we found a discrepancy when we found some heterotrophic metabolic rates in the community production, and also sometimes in the negative carbon dioxide fluxes, which might sound contrary. And we propose different hypotheses of why could this be happening, such as sensitivity in the flow rate of the closed loop that we were using, because we used mini model, which has a gas accumulation phase. We tested if this could be happening and causing the change. Also hypothesized that it could be admitted processes. However, we are still not sure of why could we found this. Important to note that it's two different methodologies to measure two different things. And we are still in touch with other scientists that also found this discrepancy. So the conclusion is that more studies is necessary to complement these two techniques and understand them together. Now moving to the conclusions. We calculated the methane offset by calculating the net greenhouse gas axis and changing the methane emissions represented as the carbon dioxide equivalents. And the conclusion was that they just represented less than 2% of the carbon dioxide. So we can conclude that the climate mitigation potential remains extremely high. As take-home messages, vegetation was the primary driver of the greenhouse gas fluxes. The winter heat wave actually improved the climate function. System resilience was achieved. The methane offset was negligible. The sink function was stronger than the source. And the broader implications and importance of this study. This is the first study that measured both simultaneously carbon dioxide and methane fluxes of this species, and it had important implications of blue carbon strategies. Thank you for your attention. And yeah. That's a very nice contribution. Actually, also with the time. So, the idea is not to use
Presentation. Questions? I support you mentioned which one definition and
yes. Okay. Yes. For methane, we found that it was significant, the effect of temperature. But then when we tested the significance between the time points, it was not. That's why I mentioned a slight increase, has increased. But what it was significant was the interaction with the violence, but not as strong as the main driver of the movement. Yes, we had 6 replicates of the little control, 6 air, and 7 in the warming treatment, because we have the backup, and 6 per treatment. The course? Yes, they were here in the picture. It's visible. No, that's, but yeah, the length was this. Yes. Yeah, I think that's the main explanation of the result of methane. The sediment in Mallorca is really coarse sediment. We measured the grain size, and it was really big grain sizes. And this is why the organic matter doesn't stay in the sediment, and why we couldn't find difference between them. So the expression of sugars, it's what is more reported from this kind of sediment in Mediterranean, especially in wide coast, as the sugar would be kept in this kind of.
We will talk about balance and also it's very interesting to see that
Yeah, Macedonia is really known for its different strategies. Their main distribution of sediment is incredible for the carbon, it's the most studied one, the most used for conservation, and other kind of seedras like this one or Prostera that their rhizomes are thinner and they don't create like mates. It's true that they store less amount of carbon, and I would say that that's why there is less investment in studying them. But I mean, there is results that at the end, even in a winter heat wave, which is a expected phenomenon to occur more and more in the following years, they actually increase their positive functions within the carbon. So I think it's really important to open what species are being starting to see us, especially in this one, particularly for and we think I think there's a people on the and I believe that's here. Yes. Yeah, I think especially in the Balearic Coast, that this kind of setting, it's difficult to account for that. Well, could you bring me the question? I don't know. This study is a good kind of study, but we are studying in other regions. We get yes. Okay. Based on their distribution, yes. In other regions. I think it could be. Yeah. I think it could be because at the end, Macedonia, that it's habit, this is in the Mediterranean, and also these species are Mediterranean and Atlantic, but the characteristic and the morphology of these species is common in Asia and the Pacific and so in different places. So I think also the fact of the coarse sediment makes it difficult to study them. It makes it difficult to extract the course. I would say that's also a fact because we face so many difficulties taking the course, maybe your lab, because of because here the tiny rocks, so the water was going down, we had to cross them fast. So I think the novelty of this will make it easier to compare with other species that are not the most common ones that we learning, and also for environments that are not muddy, for example, that are easier to close the pores, or other places that maybe are also accessible like this one, but difficult to extract, I would say. And probably not much sense. Yeah. Thank you. Or is there like not that easy? Yeah, thank you so much for the work you decide. It was difficult. I mean, it was really shallow, so that made it see. Yeah, we had a look in a few places, and next to this there was another beach, and we also found that there was a silver meadow, but it was more in patches and mixed with other meadows. Posidonia, so for having a more stable context, which is this one. It's easy because also you can hear, and I said that you have closed movement. The locks here were not allowing a lot of water flow, so it wasn't like a wavy place or anything like that. Yeah, so the sediment was really coarse. So for putting the course, the spray, but then when you take it and you put the liquid underneath, we first have to cover it. And these difficulties are the reason of why the number of courses unbalanced. We took the two backups because when we were doing it, we lost so many, right? So we said, okay, let's take two more in case we drive to the lab, we lose more course. And it happened, and we lose some part. So that's why we kept one extra in case that during the days we arrived and we have lost course. And for your yeah. The course had the water, and we put inside. Inside the course, there was a bottling stove. Yeah, they were. Yes. But before evening, yes. And the water box that was turned and it's was the same from the port. Before integrating, we changed the water that the reservoir was got, so it was not biased of recovery hospital 5 days. Water to it. Like every time they were able to change, we would make it change. Yeah, I was wondering about the choice of that. Yeah. It's within the tolerance range. So the studies that you can find on stressful frequencies are always under the thermal range, and that's why it's really common to find stressors and effects. But there is not real studies on how a thermal shock within the thermal range will affect. And finding that it was every time more recurrent to find this kind of winter increase of temperatures, but we also need during winter suddenly in 2 days 6 more grades. And how could this fast increase, especially this shallow habitat, really shallow, affect within the thermal range? And using the baseline temperature was based on the data we sampled. It was a increase. So the same. And so thank you very much. Actually picking up on that, and so like yeah, by looking at the picture that you sent over there, it's quite shallow, and the metal also is there as well. And so I was wondering like what would it change if we had samples somewhere else that was trying to get more that what I know I would say that I wouldn't say it would change the thermal range, but I think the fact that it's in winter will affect similar in different places. Like in winter is when they are in the stage that they are smaller, they are growing, in general they are like in their lower activity, preparing for the colonization. We actually went 1 month later and we could see a really big difference on the meter that is really good. So I think, for example, in the beach that was next to this one, and we also found it in the next patches, the size was the same. So I think it's more according to the life cycle in winter than actually the depth of the plates.
And then lastly, you talked about the period that's more especially there, and then just subsequently like the more activity. How would you be able to compare that?
Yeah, that would be amazing research for the study to measure that. I would say taking water samples from the sediment, like for water analysis, for example, and then analyzing the sequencing, try to find the activity of the expansion to the approach. And other kinds of sediment analysis where we could maybe separate all the organic matter and lava sugars and everything we find from the sediment, and again analyze this water. Thank you. Thank you.
My magic.
Yes.
In the machine, we used to indicate to the person that presents when it's like 1 minute left, but I think you will not be able to see me because you will be presenting.
Yes, exactly.
Do you want me to say something, or do you prefer to control the time yourself?
You can give me a sign. You can say something. I'm also controlling the time, but I might not be able to look at it, so you can just give me say something.
You want a sign when it's 1 minute left?
Yeah, you can wave.
Okay, I will wave like this.
Yeah, when it's 2 minutes, just wave, please.
Okay, 2 minutes I don't wave, and 1 minute 2 minutes I do this.
Yeah.
Excellent.
Thank you.
Good. From my side, your team's good.
Excellent. When you want to see.
Okay. Hello, everyone. I'm Tosin Sarah Fashagba, and this is my thesis presentation. My topic is evaluating how sediment characteristics influence microplastic composition in the North Sea, a methodological comparison of microplastics quantification method. Now let's dive into the background. We talk about global plastic pollution. Global plastic pollution has increased in the recent decades from about 2 million metric tons in 1950 to over 400 million metric tons in the year 2022. Plastic waste is primarily driven by anthropogenic activities. And once plastic is introduced into the environment, they progressively fragment. This fragmentation actually leads to the formation of microplastics. And then these microplastics are usually less than 5 millimeter in size. Microplastic can also be classified into they can be classified into two based on their origin. We have the primary microplastics, which are usually produced intentionally in this form from the industry, and we have the secondary microplastics, which usually degrade from other plastics. Now to the common microplastic shapes found in the environment. We have the fragments, they're actually the secondary microplastic with irregular shapes. We have the pellets, nearly spherical, and they are primary microplastics. Then we have the film, the foam, and the fiber, all secondary microplastics. Now, let's talk about marine sediment as a reservoir. Studies have actually shown that marine sediment are sinks for microplastics. When microplastics occur in the water column, because they are lightweight, their settling actually depends on some factors. We talk about the environmental factors. Example is the hydrodynamic condition or sediment characteristics, or the biological factors. We talk about the biofouling, or the particle-specific factors. We talk about the particle size, shape, or density. Microplastic does not just occur on the sediment surface, they also occur in the deeper sediment layers. This brings us to the next slide, vertical distribution of microplastics. Now, microplastics, studies have shown that microplastics are not uniformly distributed in sediments. Some authors have actually reported higher abundance in the surface, while some authors also report peak abundance in deeper layers. And other authors have also reported no patterns at all. So why do we have this? This can be attributed to the biological mechanism, probably due to the bioturbators, which usually rework the sediment, and while they rework the sediment, they redistribute the microplastic through the sediments. It can also be because of the physical mechanism, such as the waves, the tides, the currents, that can actually resuspend already buried sediments and transfer them to other locations. Now, we talk about the sediment characteristics of microplastic accumulation. Studies have also shown that sediment characteristics might actually influence microplastic abundance. But however, this is not consistent across studies. There might be other factors responsible for this, like the hydrodynamic conditions present in that region. It is also important to say that while sediment characteristics can actually influence microplastic abundance, the reported abundance of microplastic in a particular environment can actually be affected by the microplastic quantification method. This then brings us to the side. Measuring microplastic. Does the method matter? Actually, now in literature, there is currently no standard procedure for measuring microplastics. There are different different methods for microplastic identification and quantification today. On the right is just a group of how they are classified. And this actually makes it very challenging to actually compare microplastic data sets. Now, the aims and objective of this study is to investigate microplastic composition in terms of the mean and borders and morphological characteristics, to investigate the influence of sediment characteristics. In this study, the sediment characteristics we look at are the total organic matter and the sediment grain size. To investigate spatial and vertical distribution of microplastic across the stations, and to compare results from microscopy-based analysis with the micro-FTL hardware count, which was actually performed by Panto et al. In a study in 2025. Now we move to the methodology. For the experimental workflow, now to the sample location and sample collection. Actually, in this study, from the sample, two stations were actually chosen, the Belgian part of the North Sea and the Wadden Sea. And then for sample collection, like I mentioned earlier, the sample used for this study were already collected in March 2020 during the research cruise in the Mediterranean Sea and the East Atlantic Ocean. This was done by research by Panto et al. 2025, apparently my supervisor. A mini core was actually used to collect the sediment. And after collecting the sediment, it was sliced to 1 centimeter layer up to the 3rd centimeter. When this was done, the samples for the microplastics were taken and put on an aluminium foil and stored at 20 degrees Celsius. Also, sample for the TOM and sediment grain size was also taken. For the sediment grain size, a master sizer laser diffraction was used, and while for the TOM, they made use of the loss on Englishman method. I will actually explain deeply on the microplastic extraction. These are the following procedures used, which I will explain on the next slide. Now for the blank controls. The blank controls was used in the microplastic. We had two major blank controls. We had the procedural blank, which was made of sodium iodide, which means that during this procedure, just the sodium iodide was used for the extraction procedure. And then we have the hair control, in which there was a petri dish and a filter, and this was open to air in the lab for the period of the microplastic extraction. Now, before extraction and identification, we took out the sample from the freezer and allowed it to thaw for 1 hour before starting. Then we actually homogenized with a clean spatula, and then we weighed 6 grams of the sample. This was then put into the Falcon tube, and sodium iodide was added for density separation. After this, centrifugation was done 3 times, and then after each centrifugation, we had to filter the supernatant carefully in the filtration system. After the filtration, the filter paper was carefully removed from the filtration, placed in a beaker containing potassium hydroxide, and this was digested to remove organic matter. Then, after the digestion, we had to remove the filter paper, rinse with milky water, and make sure that we had to filter the digestate in the beaker into a micro sieve, which was 25 micrometer, and this was then washed into the filtration system again to capture the microplastic. At the end of this, at the end, we had to take the filter paper, place it in the petri dish, cover it with the lid to prevent contamination, and then we take it to the microscopy to identify, quantify, and data analysis. Now we move to the results and discussion. For the blank controls, for the procedural blank, we actually found 2 blue fibers and 1 yellow fragment. And then for the air control, just 2 blue fibers. So because there was limited contamination, no correction was applied to the data set. However, this should be kept in mind when interpreting the results. Now for the mean abundance. You can see the graph on this side, just to show the mean abundance in the stations. The station 6 is actually the Belgian part of the North Sea, and the station 8 is the Wadden Sea. We can see that the Wadden Sea has a higher mean abundance compared to the Belgian part of the North Sea. This is just a descriptive, and this was actually the significance from the ANOVA, which I will show in the other slides. Now we also look at the microplastic shape and color categories, like I mentioned in the objective. And we take a look at the left-hand side, the Belgian part of the North Sea. You can see that each of the layers for the Belgian part actually contains more of blue fibers. And when we look more, that's the shape. And when we look at the color, it has a limited color diversity with just 4 colors. And also, we also notice that in the intermediate layer, the pellet is actually missing. It's not there. So one thing we can draw from here is that microplastic shape often give us an idea of the source of pollution. So in the Belgian part of the North Sea, since we have fibers, we can say that since fibers are actually from synthetic textiles and they are released during laundry, so we have pollution here from the waste effluents or from maritime activities. And then when we talk about the Wadden Sea, we also see that the purple film actually dominates the upper layer, and we have the blue fiber dominating the intermediate and deeper layers. When we talk about color diversity, you see there are much more colors in the Wadden Sea. So when we look at the source of pollution here, we can also attribute the film because film was actually the one that dominates the station. Then we can say even at the Wadden Sea, it's actually dominated by the input and degradation of plastic bag. and some packaging materials, and also even from fibers, which is from waste effluents and maritime activities. Now let's talk about the result from sediment properties and microplastic accumulation. This is a PACA that shows us the sediment characteristics. And remember before I said we're actually looking at the cohorts and the grain size. So in our study for the grain size, normally we have the cohorts, the clay, and the slits. But then at the end, I actually match the clay and the slits together and call it the fine sediment fraction. So for the cohort sediment, when you look at the graph, this is station 6. Is actually the Belgian part is actually correlated to the cohort sediment fraction. And then this is station 8, the Wading Sea, which is more correlated to the total organic matter and fine sediment fraction. Then, having found these characteristics, we want to predict which of these factors actually influence accumulate microplastic abundance. And then from here, we see that the fine sediments and the station, there was an interaction. Since there was an interaction, I went further to do an HEMIS. This is the negative GLM, general linear model. And then the HEMIS shows that the fine sediments actually influence microplastic abundance in the Wading Sea compared to the Belgian part of the North Sea. So why does fine sediment behave this way? Literature has shown that fine sediments are usually found in low energy depositional areas. They are small particles clustered together and they actually have low permeability. So, and they have a large surface area which allow them to trap microplastics. However, some studies this study, actually the pattern seen in this study also align with other studies, although some other studies have also seen otherwise. Now we move to the spatial and vertical distribution of microplastics. When you look at this graph, you will see that this is the Belgian part of the North Sea, and then this is actually giving us an idea of the vertical distribution. You see that there is a decline from the upper layer to the deeper layer. But when you look at the Wading Sea, which is the station 8, you see there is a peak abundance in the intermediate layer. Now, I talked about before the physical sediment mixing or bioturbation, which might be responsible for this. Then we went further to the ANOVA to see if there is actually a significant. Like I said before, the Wading Sea has more microplastic compared to the Belgian part of the North Sea. And when we look at the depth vertical distribution overall, the upper layer has a higher abundance compared to the deeper layer. So why do we have this? We can say that in the Wading Sea, probably the environmental conditions actually favor microplastic abundance, or also anthropogenic activities. If you remember, I will take you to the previous slide, which is the PCA. I said the Wading Sea is more correlated to TOM and fine sediment fraction. And then when we predicted it, it was the fine sediment fraction that likely promotes microplastic abundance. So we can say that in the Wading Sea, microplastic abundance is likely driven to the presence of the fine sediment fraction. And also for the vertical variation, we can also say this might be the influence of bioturbators activity. Now for the methodological comparison, looking at this graph, like I said, we compare the method of microscopy in this method with the method of we use the micro FTIR. We found an interaction between the method and station. So we went to look at the HEMIS, and I see that I checked the HEMIS and looked at the different method at the different stations. When we look at the Belgian part of the North Sea, which is the station 6, we see that the FTIR here was higher than the microscopic count. However, it was significant. But the station 8, FTIR was less, but it was not significant. So why do we have this? We know that methodology in microplastic is a common topic and it's actually a challenge. This, I actually think I attributed this to the limitations of this method, because both methods have limitation. When you talk about FTIR, it's actually good for identifying polymers, but then it can actually result into overestimation when there is a single particle and it reads at different size, or underestimation when you have a cluster of particles and it only reads it as one particle. And also microscopy is inexpensive and it's widely used, but then it's prone to human error, whereby we human can actually sometimes miss some particle or sometimes count particles multiple times. Other studies have also reported such of this. in their method, in their trends. Now to conclude, the takeaway message from here is the Wadden Sea actually showed microplastic abundance was higher in the Wadden Sea, and this was due to the fine sediment fraction. Also, microplastic was detected in all layers with a general decrease in the depth. And then for the methodology, we said the microHFTR was higher than the microscopy in the Belgian part of the North Sea, and this allied the importance of having a standard operating procedure. Therefore, future research should actually focus on additional environmental factors such as hydrodynamic conditions or probably the sediment characteristics that was not looked at in this study, and also look into the deeper layers to see how far microplastic can go and eventually development of a standard operating procedure. I would like to acknowledge Imbisi, Ghent University, and University of Agra to say a big thank you, and also to my supervisor. Thank you. And questions are welcome.
Thanks a lot. Thanks a lot for your talk. You respected the time. So maybe now we start with Heidi.
Sure.
Or a few questions.
Hi, Tosin. Well done on your presentation. Thanks very much. I just have a few more like technical questions. As you know, with the lot of information and kind of quick, sometimes it's kind of hard to catch up. I wanted to know. So you said you were doing 1 centimeter layers, but what was the total depth? So like, how many layers would you have looked at?
Yeah, I have. That was 3 layers: 0 to 1. 1 to 2, 2 to 3. It was sliced at 1 centimeter intervals up to the 3rd centimeter.
Okay, and did you expect to see much difference in that depth, you think, in the
Yeah. Before I started, I expect to see, because I read from literature about the activities of the benthic organism, which are the bioturbators. So, but from literature, I also read that it decreases. And also some other studies also reported that sometimes they don't find a pattern. And some studies find peak abundance even in the deeper layers. So it's kind of different kind of theories in literature.
Okay. Then could you tell me again how you did your field blanks?
My what?
Your field blanks?
My blanks, I had 2 blanks. I had a procedural blank, which was the sodium iodide. Majorly, I just used the sodium iodide and went through all the extraction procedures, which I explained. I can put back on my slide, please. Yeah. So I went through all this. Oh, sorry. Yeah, so for the blanks, I just used sodium iodide, put it in the Falcon tube, and then did the procedures. Why for the air blank, I had a petri dish. There was a filter there. I placed it on my the table I worked with, and I was busy extracting, and I left it there for the period of extraction. When I was done, I had to cover it and then view it under the microscope.
Yeah, so on that air blank that you did, you got some blue fibers as well.
Yes, I got some. That was why I mentioned that when interpreting this result, it has to be kept into consideration. But though it was 2 blue fibers.
But you didn't use a correction factor anyway for those.
I'm sorry. What do you say?
You didn't use a correction factor anyway to take into account those fibers, because you found a lot of blue fibers as well in your samples.
Yes, I found a lot of blue fibers, but I didn't deduct it from the sample because it was still limited, not something so much based on literature, but I just had to report it that when interpreting the result, we should keep this in mind.
Okay. And then probably lastly, did you measure the microplastics that you found or no?
Yes, I did. And I actually reported that in my manuscript because there was no significance. I didn't report that here. I actually measured my microplastics, the size, and then I checked if the size I got which I grouped in the size class. I checked if it was different with layers, but then there was no difference. So that was why I didn't bother to include that.
Okay, thanks very much.
Thank you.
Thank you, Tosin, for your presentation and for the research you've been doing. Yeah, I was also wondering for the methodology. Like, it's a big challenge in microplastic research, and I wanted to hear from you, from your own experience. Actually, what are the biggest challenges throughout this protocol of extracting microplastics and filtering? And what are the limitations that you have to face?
Okay, if you ask me, you mean the procedure of extraction?
Yes.
One thing about it was about being clean, because I wouldn't want to introduce external microplastics into my sample. I had to make sure to keep a good workstation to make sure everything was clean. And also, that's for the extraction. And one thing again I noticed was doing my viewing on the microscope. This was very, very, because the microscope takes time, it deals with a lot of concentration. You have to, and also be able to confirm it's a plastic. So even after I was done confirming, I had to do a hot needle test to see if these are really plastics. So these are the kind of things I actually encountered during my procedures.
Mm-hmm. And now, after you've done this for quite some time, would you have some recommendation or improving the protocol or some idea of how you could do this better, more accurate?
Yeah, I think if I want to do this next time more accurate, because microplastics have this heterogeneity structure. They are usually patchy, not homogeneous. So I think if I want to do this next time, I would like to have samples from different sampling sites in the region, not 3, but more sampling sites, so to capture the microplastic abundance due to the heterogeneity nature. And also, not just picking microplastics just once, I also think to do it in seasons. So we can actually evaluate in the different seasons how do these microplastics accumulate in the sediment.
Yeah, that's very interesting. And also, last one, just for the depth that you mentioned, also about bioaggregation of organisms in the sediment, that indeed is very important to redistribute the microplastics. I was also wondering if that is related with the type of microplastics. So if we're talking about fiber or other type, would you expect that they are all redistributed in the deeper layers, or no? It depends on the type, maybe.
So thanks for the question, because it's interesting, because actually I found almost all type of microplastics in the deep layers. So it doesn't in terms of shape, I found almost all the shape in the deep, except for the intermediate layer in the Wadden Sea where pellet was not found. But in the other layers, I found most all microplastics are there except for the intermediate. So through the reworking of the sediments, this microplastic, because they have to feed, they have to dig the tunnels, and then the microplastics go down. And sometimes even, like I said, the physical sediments mixing also we suspend, and then they still settle back again.
All right, thank you very much.
Thank you.
Patricia, if you have a quick
Thank
question.
you. Yes. Let me go to my notes. Some curiosities. And it was also with the controls, but we talked already. In terms of the lab coat, any cares or gloves or without gloves, because some people use lab coats of a different color in case some fiber appears, for instance.
Okay, thank you. Also for the lab coat, I actually used a cotton lab coat, because cotton lab coats help to prevent the introductions of synthetic fibers into the sample. And then for the gloves, I didn't use a glove, but I made sure I always wash my hands before starting, and also use the ethanol, because I use ethanol to clean the surface, wash my hands, and use my hands.
Very well. And the curiosity is, this was a lot of samples, so I see that then you analyze also by FTIR, but not chemical analysis, I think.
Sorry, I didn't get you.
That will be a lot of samples. For curiosity, how many samples, and in microsphere if there was any. It's not background. It's that sometimes we have fibers on top of each other that we cannot see. It's more upground than background. Yeah.
Yeah, sorry, I missed your question. I don't understand it.
It was several. Yeah, you did not do analysis by the field of chemical analysis.
No,
Only
I didn't do chemical analysis. Actually, like I said, the sediment sample I used was already used from a previous study by Panto et al., which was my supervisor, and she made use of FT I have. That is the micro FT I have. And then I make use of the microscopy to compare results. So I compared my result with a result in terms of quantification and not polymer types.
Yes, yes, yes. Okay.
Okay, thank you.
And that was it. Yeah. I don't want to over the time.
Hi, Tosin. I have a question maybe, so as I am the end, I'm going to go maybe more specific. On your slide 17, 17, you're using a PCA. And if you can come back on slide 17. Yeah, that's one. Yes. I'm curious about the use of this PCA, why you're doing that, because I see that there are 3 variables, including 2, which are very correlated. So what was the main objective of using a PCA here?
Okay, like I said in the beginning, like I wanted to look at the sediment properties. So before I can look at these predicting factors, I had to take my sediments and look at the data to see which sediment do they have. So I did a PCA based on the data I have for the sediments characteristic. There was a data with my stations, the different sediments, the TOM, the fine. There's the fine and the cohas. So now, and I wanted to see for the Belgian part of the North Sea, what type of sediment does it have? And for the Wadden Sea, what type of sediment does it have? So the PCA here actually helps me to group the sediment characteristics based on the station. That is why when you look at it, the Belgian part of the North Sea, the pointer is not here. Which is the red, is more correlated to the cohas, and then the Wadden Sea is more correlated to the TOM and fine sediment fraction. So probably this is why in the Belgian part of the North Sea, it does not have much microplastic abundance because cohas materials have large pores and they have a high permeability compared to the Wadden Sea, whereby they have clustered and low permeability and can't flush microplastic out.
Okay, I better see the point. Thank you. And maybe a last question, which is more general. Yes. It's I'm just curious about, because you're talking about 2 methods, the need to have a standardized approach. It's clear. Do you know the proportion of how much the 2 methods are used? Generally.
What do you mean?
Like the 2 methods that you're comparing here. Do you know the proportion of use of these 2 methods in the scientific community currently?
Wait, I don't get a question. Are you asking what is microscopy used for and micro FTIR?
I don't know if you can hear us very well. Christophe is asking if you are aware of the proportion of use of microscopy versus FTIR in the microplastic field.
Yeah. From what I understand, for the proportion, because the word proportion, I don't get the proportion you mean, but I understand how we use the microscopy and the micro FTIR, because the microscopy, the optical microscope, gives us the morphological characteristics. Is that what, like the morphology, the quantification, when you talk about the FTIR, normally FTIR just give you the polymer types. But because now we have the developments of the micro, which is like the imaging attached to it, we can also see the morphological characteristics like the shape, the color, and the size. Yeah.
Okay. Thank you.
Okay. Thank you. Thanks a lot.
Thank you.
So that would be our last one of the morning. Group session, like you shall be presenting the webinar on the behavioral microphone, or just I'll just project my voice. Okay. Yeah. Thank you. Okay. So, hi everyone. My name is Patricia. I was supervised by Dr. Maria Perez-Tadeo at the Atlantic Technological University in Galway, Ireland, and this topic is looking at the effects of underwater noise levels on the acoustic behavior of dolphins in the North Channel. Now, where is noise coming from? So there are many sources of noise in the ocean, being of both origins in natural or anthropogenic. And anthropogenic noise is an increasing concern as there is increased input and intensity of this type of noise in the ocean. That has far-reaching effects on marine life because it can travel a lot faster and farther in water. Just a few sources of anthropogenic noise of concern are different types of vessels, sonar, seismic surveys, and then some sites where there is more elevated noise in intensity. I am focusing on the Straits, and as there are many other ones, as the Straits is more of a topic of my thesis. And on that note, the study site is the North Channel, which is a strait, which is defined as this narrow passage where there is very heavy shipping traffic. And in this case, it also provides a biological connection between essential habitats for many different cetacean species. And I wanted to highlight these two species here, the common dolphin and the bottlenose dolphin, that have been cited in this region, as they are also awarded extra levels of protections within Annex 2 of the Habitats Directive. And just a note, I do not have specified species as a part of my study, as it's more general. So I just wanted to say that as these are cited in the region, they are likely contributing to the data that I will be explaining further. And to have a visual kind of representation of just how many vessels can be present at any one time, and you can see just how concentrated they are along coastlines and some of these straits where we have narrow passages. And then an important note about vessels in particular is that they have very high noise energy concentrated at low frequencies, below 1,000 hertz. Now, some impacts of noise, of elevated noise on dolphins. For one, can be that they avoid certain area that might be their essential habitats and important to them. It can also lead to strandings of dolphins or hearing damage, depending on their proximity to the elevated noise. And then for more focus, what I'm focusing on is the impact on communication, as they are very social species, and sound is very important in their communication. It's very complex, the way that they communicate. And I will just touch on a few things in here. That is the way that dolphins use sound. They have a very, very wide range of their hearing capacity. And so very high capacity to negatively impact captive by noise within like such a large range of frequency that they can take in. And as I'm focusing on whistling, in terms of their communication, we have a few different forms of communication, but whistling in particular can range between typically 2 to 20 kilohertz, give or take a bit. And then also some associated behaviors that are directly associated with whistling communication are like socialization, group cohesion, and feeding. So some very vital behaviors. And then direct impacts of noise on their whistling behavior has been shown that like they are able to adapt the way that they whistle, so they can adjust their whistle frequencies, for example, increasing or decreasing in relation to where there is less noise interference to be better heard by other individuals that are trying to communicate with. And so now on to my research question. I'm looking at how is dolphin whistle behavior affected in relation to underwater sound pressure levels in the North Channel. And so sound pressure levels is basically a measurement of noise measured in decibels that I am going to be touching on throughout the rest of this presentation. And so to answer this question, I designed two different bands of sound pressure level. The first one being termed the low band, which encompasses the lower frequency range, and looking at the noise level in that lower frequency of 63 to 1,000 hertz, as that is more representative of where there is more concentration of noise from shipping traffic. And then I also looked at a broader frequency range, looking at the mean noise level in decibels between about like 1,000 hertz to 25,000 hertz, as that was encompassing the frequency range that I saw in my data that I extracted. And then I have a lot of response variables that I will touch on more in the next slides to insert my research. And so now with the methodology, so my data came from two different static acoustic monitoring devices that were deployed in the North Channel that you can see in the diagram above here. And this was part of a larger project called the Straits Project that was designed to map like the levels of noise in different straits around Europe and potential impacts on cetaceans. And then I passed specifications on the deployment of the devices that I don't get into all that detail right now, but just a few things to note is that they were continuously recording or taking audio recordings with a duty cycle of 15 minutes for every hour in the day. And as like this ended up being many hours of recordings that were used from these devices. So for the methodology that to be able to concisely go through and like be able to find whistles to answer my question. But luckily there were FPOT microphones that were paired with these devices that are able to detect the presence of whistles based on if they're echolocating or not. So it can say they're echolocating whistles, so they're likely. So I could target like certain days and times where there were detections of dolphins that give a better chance of finding whistles. So for my response variables, I have quite a lot, and a few of them are all different measurements of frequency. And so I have a visual representation here that the minimum you can see is the lowest point of the whistle contour here. And then the maximum is the highest point with the start frequency at the beginning of the whistle and then end at the end point of the whistle. And then my delta frequency is the change in the frequency between the minimum and the maximum. And then the peak frequency is looking at the points in the whistle where there's the highest amplitude, the highest energy of the signal. And then I also look at duration, which is the length of the whistle in seconds, which you see here. And inflection points, which are the turning points where the slope of the whistle will change. So here. And then lastly, I looked at shape of the whistle, which is essentially looking at the change of frequency over time. Now, this is the program that I used to extract my data from the audio recording. So this is a spectrogram in Raven Pro that is a visual representation of these recordings, looking at like the change in frequency on the vertical axis in relation to time. And then it also includes the energy of the signal in terms of like how bold the signal is. So like the darker area to higher amplitude and energy of these signals. Some selections that I made of whistles. And then just for visual representation of the shape categories, I chose 6 general shape categories that you can see over here. And it is showing the change in the frequency over time, and they were all categories of these general shapes. And now, part of my methodology to determine the best selections to extract to have like a more standardized approach and have like a bit more accurate data is I developed the quality selection criteria for which whistles I was selecting. And so for one, they had to be clearly visible and bold enough against the background noise. They needed to have a start and end of the whistle that was clear and not be overlapping with other signals. And an example of one said good quality whistle that there's one that is selected is actually top for again, it's the quality selection criteria, and then the next two examples is that ones where they are overlapping or dates where you can still kind of see. Now onto results. So I am still in the analysis phase of my thesis, so I'm presenting more preliminary results at the moment, and to have an idea of what my data looks like. So I ended up analyzing a total of 61 sound file recordings, with 18 of which of them had good quality whistles that I could extract from. And I ended up with a total of 178 whistle selections that I extracted with all of the response variables that I mentioned. And then the frequencies of these whistles were ranging to nearly 4,000 to 23,000 hertz. The ratio of whistles that I saw was ranging between about half a second to 1 to 4 seconds. And then visually, a figure of the total number of whistles that were assigned to each general category of shape. So the most prevalent one that I saw was this one here, is the downsweep. So it was where there was a descending frequency and changed over time in the whistle contour. And then for this diagram over here, it's for the inflection points. So the vast majority of the whistles either had no inflection point and had like one constant slope frequency over time, or one. There's more preliminary kind of figures. I plotted like the general relationship between some of my response variables and the sound pressure level, so the noise level in decibels. That I'm just gonna point to one of these so I can kind of better explain it, so we can focus in one area. So over here, I was looking at the minimum frequency on the y-axis, and along the x-axis sound pressure level in decibels, and increasing this way. And so my hypothesis would have been that with increasing sound level, I would expect to see a linear relationship with increase in frequency of my data points based on the available literature knowledge that is already out there. But however, in my data, it might look a little strange. I have one level of sound pressure level where there were so many more data points, as I had one recording where there was just a lot more whistles and a lot more data that I extracted from that recording that were of the good quality that I extracted. So it does make the data a little bit more unbalanced in a statistical standpoint. So I'm currently still working on like the modeling that's representing my data statistically. And as I do have a lot of response variables, I would just isolate a few. So I have the minimum frequency, maximum frequency, and duration of the whistle, and I would be able to be confident to say visually if there's any trends in my data at this point. And then this is kind of a similar, like in the previous one, I was looking at the low band SPL data, and this is the broadband, encompassing a larger frequency range where whistles are visible, or whistles are where result is whistling in this frequency range. So the data looks to be a little bit different, more on the lower decibel range, but still I didn't say any kind of trends just in the data. So I have a few more figures looking at like categorical variables, like relationship with the noise level. So this was just to kind of visually see like the spread of my data across like the noise levels. So like for example, the whistle shapes, like for this one, just to explain, like this whistle shape A was seen across the whole range of noise data that I had, but was a lot more concentrated at this one value as mentioned in the previous diagrams. That meant that would be unbalanced. So it's kind of similar idea of this inflection points in this figure over here. And then some points that I'm currently working on for analysis is I'm trying to applying generalized linear models, likely with a mixed model effects, adding some potential random effects as such as the station from which the recording is from. I also had there was a high correlation between my low and broadband SPL data, so I modeled them separately against the response variables and potentially including some additional some covariates that might influence the variance in my data, such as that those type state, so long as there's no collinearity with my SPL data. So those are my plans for my continued analysis, and then some limitations of my thesis that I can maybe discuss further if I'm near the end. But like the manual selection of the whistle was very time consuming, so I didn't end up really extracting as much data as I would have liked, and maybe why my data looks a bit more unbalanced in this stage right now. And identification of the dolphin species was possible, so it's more general saying dolphin species. And background noise could potentially be masking whistles, so it's possible that that at very high noise levels that you're not seeing the whistles that dolphins might be trying to communicate. So then maybe that's missing gaps in the data that we can properly see, but at high levels of noise, how it's whistle changing, and see the whistles and visually and stuff. And there's other factors such as behavioral state that could heavily influence their different characteristics of the whistle that they would need to be cared with in the surveys in addition to their face recording devices. So I can finish it up with some potential areas of improvement to continue this project would be filtering out background noise from the whistle selections to have potentially include other frequency parameters or just have better quality data, like reducing that masking effect from background noise, and also potentially improving signs of associated categories as that was more visual and maybe somewhat subjective to kind of categorization as well as data processing for whistle quality selections. So thank you for your attention. Appreciate it very much for your presentation. I think my questions are a bit more general. First of all, I definitely consider you the conclusion of the use of external extractions, right? But I was trying to understand by looking at the cycle of just wash where exactly okay. So we have effects of underwater noise levels and dolphins in the ocean. So first of all, how we incorporate the underwater noise there, because what you showed, we're just looking at the research from the dolphins. The underwater noise was it was already calculated by my supervisor from the same audio recordings from which I looked at the whistles. And so I had that data set that I then created those bands that I mentioned, like the low frequency band of SPL and then the more broadband. So I created I calculated the mean noise level within those two bands to see if there's an effect on increased noise level on the whistle characteristics from that noise. Yeah, so that's the figures that I showed was the joint data of the those like new SPL bands in decibels against the response variables.
Can you state that for your selection of the whistle that you say that you were selecting them as a goal overlap with other CEOs? So, like, how does that not affect as well? If you're looking at background noise as well, and it's like, you know, what the reality overlap, so you're breaking out the one that will overlap. And how does that
In terms of that, maybe I'm missing some data, you mean, because I'm skipping those? I guess the main idea of like, well, to answer the question was more to look at the direct impact of like whistles that were very well and visible, and the problem with like the overlapping ones is it would, I wouldn't be able to properly extract some of these like it would be hard to define where the start and end of one whistle is. Like I wouldn't be able to distinguish whistles apart. So like in terms of the variables that I was looking at, it wouldn't be possible to extract that if I was trying to select all the overlapping ones. So I view that as something that I was thinking about too when I really was starting my thesis, that I felt like I'd been missing data if I was skipping this, because there were definitely a lot of recordings where I had a lot of like overlapping whistles, but I guess to keep it kind of standardized, like to try to have the best quality whistles as possible, because I mean, just like I mentioned, the faint whistles that I didn't look at because they weren't good enough. I saw a lot of that too, that it could end up being that I was looking at the fragment of the whistle. Maybe the dolphin wasn't directed at the recording device very well, that it's not properly keeping up with the full signal. That I am missing that data too, but it's not so much like the count of whistles that I'm not looking at that. It's more like the whistles that are there that are clearly visible and I can analyze, like how might that be changing with different noise levels, and like higher noise is that increasing the frequency and decreasing the frequency.
how would you incorporate behavior?
So when I like for the type or like the question, like behavior kind of encompasses all these response variables, like the frequency, it's and the shape of the whistle as well. Because it's like dolphin communication is so complex, and like it's just like certain parameters that I looked at, for example, just the shape has been associated with certain behaviors that maybe, like, for example, I can't think exact, but like a rising, like an upsweep where there was a rising frequency over time, like might be associated more so with social interactions, for example. So a lot of like their behaviors can be associated with some of these specific parameters within like the whistle selection that I made.
First of all, like setting our
That's also something that would be difficult in this analysis, as far as I understand, to be able to. That's also something I'm thinking about in terms of like how my data works statistically, like that that my data is likely not independent, like my like sample, like whistle selection, because I can't say if it's the same individual using a few of these whistles or how many individuals there are producing whistles and recording. And as far as I understood so far, there and like literature I've looked at, I don't see a way without like accompanying visual surveys of seeing the dolphins while they're producing these whistles. I have seen studies where they've accompanied, maybe looking at the presence of both in addition to noise levels, but actively recording as they're watching the behaviors to of the dolphins. Yeah, as far as I'm understanding so far, I think it wouldn't be possible maybe without some accompanied like visual sightings. Right. Yeah, that's. Yeah, that's a really good like point because I was thinking that exactly when I like started is like I didn't like the idea of skipping those because I was like maybe that's a response to a very loud noise. I remember actually the reporting that had so many data points that I saw like where you saw it put my data was kind of imbalanced like that line. Like there was a period of time where it was very, very loud now that I'm remembering and after that kind of quieted down a bit, there was a lot of whistles and they were like overlapping each other like that. So potentially like they were kind of in an almost like frenzy of like trying to communicate and now it's like, oh, it's a bit quieter, we can hear each other like and like what's happening, maybe we're lost and I don't know, but that's so yeah, I would have it would have been nice maybe to include that, but it's so difficult to say distinguish whistles apart from each other, so I wouldn't be able to extract like any of those whistle frequency parameters or like shape or anything like that. Or it would be more. It just wouldn't be very standardized, I guess. And yeah. Yeah, so yeah, at like the low band. Yeah. So that's good question. So as like dolphins have like a very wide range of like hearing capacity within like frequency range, they also have different sensitivities depending on where like what frequency this noise level is at. So for example, at this like low band that I'm looking at that went up to 100 decibels, their hearing is less sensitive, so they can tolerate higher decibels. I can't think of, I mean that also varies maybe by species too as well, yeah, but they have there are like these thresholds where they might end up getting some kind of damage, but they can recover. And then there's this other term of like more permanent kind of threshold where they will get hearing damage from if it's a certain decibel, but it depends like what frequency this noise level is at because they're more sensitive at higher frequencies. So if you're looking at maybe like 50 kilohertz, if you have like 100 decibels there, it would have a bigger impact on them than like at these low frequencies of like 1,000 hertz because they're a lot more sensitive at higher frequencies. Yes. Yeah, so that's like the like the whistle shape categories is like an example of like these two here you have a one and it's like this shape it starts and ups and then it's opposite over there. So that is something I right now wouldn't know how to address that, but like could like in combination with the number of complexion points that I have and the whistle shapes that it categorizes. Yeah. Like in terms of how many inflection points they have in?
Yeah.
or like what shape? As I'm understanding it, like it can be heavily associated with like specific behavior. Like maybe they're like from studies I've seen, like they might be hunting and like foraging, and then they witness a certain shape, perhaps that was a lot more prevalent than other whistle shapes. So this shape could likely be including some kind of information necessary for this behavior, and it's kind of it's no, yeah, that is something that like with signature whistles would be something that is like more of a kind of identification of one individual, and that's something I didn't really look at, but I did notice like um, some whistles that followed like a very unique shape that I wouldn't even know how to fit into any of these categories. That they repeat this when they've had studies when they're maybe separated from each other to locate each other. So they kind of have their own, each individual does have a specific signature. So yeah, this has been seen in a lot of studies, specifically on bottlenose dolphins. I believe more like experimental, like in a controlled environment. So yeah, that makes sense. Yeah. So that was why I was considering having station as like an extra factor and like kind of making a more complex like model because like there was like variance in like also like the depth at which these stations were at. Like this device is at 30 meters, and this one is at 72 meters, and so I guess I mean they're also like within a range where like dolphins could be present. So like potentially, well, station could also be seen as like maybe depth as like a factor to even like in my models. So I guess I maybe from the standpoint of why they put these two like in this kind of proximity to each other and with different recording devices, I'm not really so sure on why that was done. I guess like at one of them, like the first one, station 9, the thing with that one is like it had a much shorter deployment time than was planned because it got dislodged or like from its mooring device. So it was like found that some here like months later, but had only been deployed for a month. So I had less reporting single through from there that had dolphins that were present from detections. So that's also kind of maybe a limiting thing is that I only had a few reports from that device that I could even extract whistles from. Thanks a lot. And this is our closing our last section. And now we